This is a quick lecture on how to write nuclear equations, demonstrating natural transmutation, where the nucleus of an atom, because of instability, either through overcrowding of the nucleus, or too many neutrons, or too less neutrons, become a new atom by changing its nucleus by removing some particles, or some particles changing into others. So we'll start with cobalt 60. It's a radioisotope. Radioisotope means that it is an isotope of cobalt that is unstable. And radioisotopes or radioactive isotopes or unstable isotopes of cobalt or any other element that we use in this course is listed in table N. So let's go to table N and let's go find some cobalt. There it is, cobalt 60 in all its glory is right there. And what it shows here is the nuclide and the radioisotope, the radioactive isotope of cobalt. Now, cobalt isn't normally radioactive. At least there are some isotopes, I should say, that are not radioactive, but this one is. So these are the exact type of this atom with a mass of 60 with a certain number of neutrons, that is unstable. Any case, we call it cobalt 60. That 60 is important. It's the isotope that's specific for this radioactivity. We have its half-life, but we care about its decay mode. So it's a B negative. Now this is a beta particle. Now if you don't know that, you can go to your other reference table. Oops, I'm going the wrong way. All right, table K. And we can go to table O. All right, and table O shows us beta particles, which are high-speed electrons, have this notation, 0, -1. So I know from my table that this is a beta particle that's given off. It has high-speed electron, essentially has no mass, and this is a -1. And what happens is, to find out what particle remains or what the nucleus remains, what we do is we match the atomic numbers on the bottom with the mass numbers up top. So let's start with the mass numbers. Conservation of mass states that 0 plus some number has to equal 60. So tough math, there it's 60. And the charge numbers, these are the bottom numbers of the charge numbers or proton numbers. So what number plus a -1 is 27? Last time I checked it was 28. And now we have element 28. And now we have to find that on our reference tables, or our periodic table. So if we go to our periodic table, we'll go find element 28, and we'll see that it's nickel. And that's all there is to it. And that's Ni. And that's a completed nuclear equation showing natural, transmutation. This word transmutation is talking about the idea that the nucleus, the unstable nucleus, is becoming more stable. In this case, by giving off a beta particle, a high-speed electron, what we're saying is that a neutron, is neutral because, well, it's got basically made of a proton and an electron. Yes, there's a neutrino in there, but essentially a neutron split into a proton. That's why the proton number increased. This electron is kicked out, and if you notice, our ratio between our neutrons to protons increased. If you look 60 minus 27, we get a 3. This is a 5. 5 minus 3 is 33. So there's 33 neutrons to 27 protons in this case. Here, we had 60 minus 28. 10 minus 8 is 2. And this is 5 minus 2 is 32. So notice the neutrons went down. Well, of course they went down. A neutron split into a proton. So this is 32 neutrons in the nickel, and you've got 28 protons. So if you notice, the ratio improved. This was a high 33 to 27 ratio, now to 32 to 28. So in this case, there was too many neutrons to protons. So by a neutron splitting to a proton, we've lowered the neutron number and increased the proton number to improve that ratio. For whatever reason, having too many neutrons is unstable in a nucleus, and that's how this atom fixed itself. But all those details aren't all that important, just writing these equations. Okay, so let's look at uranium-238. Now this number is way above 83. Way above 83. So if it's way above 83, or 82, okay, we know that it's overcrowding in the nucleus. So I know this is going to give off an alpha particle, but if you didn't know that, we go back to our tables, okay, and let's go back to table N, all right, and we're going to go back to uranium-238. I'm just looking it up, okay, information we already have, okay, there it is. Look at that symbol. That's an alpha symbol. Now, if you didn't know that, okay, we go to table O, and the alpha particle gives you that. Look at the notation, 4 over 2 helium. It's got a mass of 4, 2 protons. Well, 4 minus 2 is 2 neutrons, 2 protons. So uranium-238 gives off something called an alpha particle, which essentially is 2 protons and 2 neutrons that are emitted from the nucleus, an unstable nuclei called a radioisotope. And reason why atoms give off, let's say, this particle of 2 neutrons and 2 protons called an alpha particle is because the nucleus is unstable, high energy, and it's got too many protons. So the protons are emitted to lower the proton number. Any element beyond atomic number 82 has just too many protons, too many positives in a close space that can't be held in a nucleus, they think anyway, and it makes the nucleus unstable. And to relieve that stress, protons are emitted. With it, of course, are 2 neutrons. Neutrons stabilize this repulsive interactions. So in any case, giving off a alpha particle relieves the stress, and we write that in a nuclear equation. So because there are 2 protons and 2 neutrons, and because a proton and neutron essentially have the same mass, there's a 4 written for the atomic mass of a alpha particle. And of course, there's a 2 written for the 2 protons. And you can write He to show a helium nucleus, because essentially a nucleus helium is 2 protons, 2 neutrons. You could also see it written as the alpha symbol. Any case, finishing out our nuclear equation here, as I talked about before, to do this, all you're really doing is, well, for one side, your law of conservation of mass is being held here. 4 plus what number is 238? And of course, you would write 234. So 234 plus 4 is 238. And of course, the bottom numbers here are the charge, and the charge is conserved as well. And so what number plus 2 is 92? And this, of course, is 90. Let's keep that in red, color coordinate, of course. Okay, so 90 plus 2 is 92, and 234 plus 4 is 238. And that's what you're doing in these nuclear equations. You're making sure all the numbers on the top, the mass number, equal all the numbers. Now, in this case, since it's natural transmutation, you only have one particle naturally decomposing into or transmutating, we would say. Mutation is changing its nucleus into a new element. Okay, so atomic number 90 is going to be thorium. All right, I would look on the reference table, and it's important you pick the right element for the atomic number. In any case, checking my math, I've done this correctly. What I will say is that this example, this nuclear equation here, is an example of beta decay. Okay, and we say decay because this cobalt 60 naturally changes into nickel by giving off a beta particle, which is a high-speed electron that came from a neutron. All right, and we would say that this example here is alpha decay. You need to see there. And alpha decay is because an alpha particle was emitted, and alpha and beta are the first letters in the Greek alphabet. And the reason for that is because Ernest Rutherford, among many things that he did, He was the one credited with the discovery of the first two types of radiation, and he called them alpha, okay, and beta, respectively. Moving forward, okay, and here I have potassium 37. Let's get rid of some things that are not necessary to see. Okay, so potassium 37. So where do I go? You've guessed it, table N to understand this. Okay, so we see that K42, K37 working on, is a B plus. This is called a positron emitter. And now a B plus is a different symbol. Okay, it's actually called antimatter. It's the antimatter particle of a electron. So this is a positively charged electron, believe it or not, that when colliding with electrons will annihilate themselves into energy. But that being said, we need to know what this looks like. So if you do not know, okay, we go to table O and we find that our positron is a 0, no mass electron, positive 1. This positron particle, 0, E plus 1, very strange. It's a electron with a positive 1 charge. We'll talk about that in a second. And using our nuclear equations and our conservation of mass and charge, 0 plus 37 is 37. What number and a plus 1 gives me 19? Okay, that would be atomic number 18. Atomic number 18 is argon. So again, an example of natural transmutation, as all of these are. Potassium in these two examples naturally can transmutate into different compounds based on the particle given off. Notice this is a different radioisotope, K42, and this is K37. And knowing the radioisotope, knowing the exact isotope, both of these are potassium, same atomic number, different mass, they have different problems in their instability. Now, more importantly, what the heck is this positron? Well, it's a form of antimatter. And antimatter is supposedly from the theory of the Big Bang, where we have matter was made in two forms. And if the same antimatter hits the regular matter, well, this is the opposite form of an electron. When it collides with a proton, with an electron, it will annihilate each other and give off electromagnetic radiation. That's how a positron PET scan works. But let's look closely at what's going on here. So if you notice, what's going on here is the proton number is going up. All right, well, I'm sorry, the proton number is going down. If you'll notice carefully here, we're going from 19 to 18. So in this case, a proton, all right, is emitting a positively charged tiny mass particle, positron. So it's losing its positive charge, okay? So when it lost a little bit of its mass, tiny, tiny fraction, 2/1000ths of its mass, it took its entire charge away, and what you left is a neutron. So what this nucleus did, or this nuclei did, okay, you notice it has 37, okay, atomic mass, and this is 42. So this radioisotope has really two less neutrons. There's not enough neutrons in this nucleus. All right, now to get neutrons, you should be able to subtract here. 37 minus 19, okay, is what, 18? So this has got 18 neutrons, and this one, 42 minus 19, I believe, if my math is correct, is 21 neutrons. Check that, 23. I can do this simple math. So if you notice, this isotope has too less neutrons. So there's not enough neutrons to buffer the protons. Now we think that neutrons help the protons, okay, from repelling themselves. We know there's a strong force in the nucleus that keeps them together, but the neutrons help. So with two less neutrons, this nucleus is unstable, and probably these protons, all right, are repelling themselves in the nucleus. So to fix that, what the nucleus does is it increases its ratio of neutrons to protons. And one way to do that is for a proton to become a neutron. So notice 37 minus 19 is 18 neutrons here. Okay, if I do my math correctly, and I've been known to mess up very simple math here, this is 19 neutrons. And you may say, wow, it kind of gained a neutron. Well, it's 37 minus 18. It's a better ratio. So the neutron number definitely increased and the proton number dropped because a proton became a neutron here. And that's what a positron decay is all about. It's all about fixing the nuclei of atoms that have too few neutrons to buffer the protons, and it makes it unstable. So the atom fixes itself and becomes more stable with a better proton to neutron ratio by doing that. Now over here, we have the opposite. Okay, if you notice here, 42 minus 19 is 23 neutrons after my bad math. And over here, I think I can do this. I've got 22 neutrons. So in this problem, there's too many neutrons. See, you have to have a correct neutron to proton ratio, so we think. So having too many neutrons, we have beta decay. And of course, in beta decay, a neutron, okay, gives off a high-speed electron, and a proton remains. So here, the atom fixed itself by what? Adjusting its proton to neutron ratio by what? Essentially losing a neutron, okay, and converting it into a proton. So the proton number increased and the mass number, okay, of course stayed the same, but we changed a neutron into a proton. And the ratio of protons to neutrons in this case increased. And that satisfied this problem of this radioisotope. So radioisotopes that have too many neutrons, they lose them by giving off beta particles and becoming the proton numbers increasing, and lowering their neutron numbers do so by beta decay. And by positron decay, they do so by emitting this positron. And that, of course, increases the neutron number. So yeah, it's all about essentially what's inside the nucleus and when they're made, what kind of problems they have. Now these are few and far between on the reference table, but they are there. For atoms that are lower than atomic number 82, if they're radioisotopes, they are because of the wrong number of neutrons. But if they're beyond atomic number 83, okay, notice 27's below atomic number 83, so their problem is the neutron problem. In this case, too many, that's why it's beta decay. But in this case, beyond atomic number 83, this is going to give alpha decay because they have too many protons. So you can actually make some guesses of what kind of radioisotope, what kind of emission it gives off, whether it's alpha, beta, or positron, all right, based on the number of protons. If it's beyond atomic number 83, it's going to be an alpha to get rid of the extra protons that are making the nucleus unstable. Or if it's too low of a neutron number, you're going to give off positrons to make more neutrons. Or if it's too many, you're going to lose those neutrons by beta decay. Any case, probably too much information for writing nuclear equations, but I like to think that if you know a little bit more, it makes a lot more sense. But again, all these examples are natural transmutation. How do I know? There's only one reactant. Therefore, they naturally do this, and we cannot control them. And their half-lives, okay, are something that we just have to live with. We can't control these half-lives, but they do this on their own. If you had a second reactant, forcing them to collide to make this happen, that'd be unnatural or artificial transmutation.